energy and thermodynamics of it. All right, so how does it work? Obviously, first you need the fuel, uranium-235, and I'll talk about thorium on another slide, but that's like maybe a substitute, but we really haven't implemented that yet. But so you mine 235, you gotta first enrich it, and then you gotta like kind of, I guess, machine it down to like, I think like a 1-inch cylinder, like really small. And then you stack a bunch in like a really big metal tube, and that'll be your fuel cell. And then you put that in the reactor, and the reactor usually takes about, I think I read numbers like between 100 and 200 of these fuel cells. And between each fuel cell, little control rods, because when you initiate it with fission, there's just stuff going everywhere. And so the boron kind of helps, it kind of limits the amount of radiation it produces, as well as like all the neutrons that fire off. It kind of absorbs them, so it's like a more controlled experiment. And then all of this just to heat up water and create steam and, power turbines. All right, so the actual fission of it. So the process, obviously I kind of touched on it, but basically you just, in the reactor, you basically fire a bunch of neutrons, and those neutrons hit the atoms of the uranium. Those uranium atoms split into lighter elements, releasing more neutrons, and then those hit other atoms, and it just kind of keeps doing and cascades. And most of the energy comes from the actual splitting of the atom, which is actually quite a bit. And then obviously it just keeps going on and on until it eventually reduces to, there's a lot of atoms it reduces to, but things like carbon, radium, it reduces just to lighter atoms. Okay, so types of water reactors. So in the US, we basically only use these two types of reactors. The first one, pressure water reactor. It's basically to where water at a high pressure is then pumped into the reactor. It then heats up, but since it's at a high pressure, it doesn't actually create steam. It's then put into a heat exchanger into another vessel of water, and that is the actual thing that gets heat up into steam and then powers a turbine. And boil water reactor is basically just doesn't have the high pressure fluid. It just boils the water in the reactor and then creates steam. And then for the light water, that basically just means that water in the system basically both regulates and moderates the reaction. So water does take up a couple of the neutrons that are fired off, so obviously more limiting the reaction to a controlled experiment, as well as it just regulates the temperature, because the temperature can get really hot in it. All right, and these are the two diagrams of each one. So this one right here, the pressurized water reactor. Obviously you see the water get pumped up into here. So this system right here, the pressure tank's right there, and this is the pressurized water that's heated by the, obviously the reactor. And this then heats up this water to create steam. And then for the boiling water reactor, it's basically the same thing, it's just missing that. And obviously at the end, all the water is recondensed and then reused in the system. All right, so as I said before, if it looks familiar, it's just basically a Rankine cycle. Just replace the heating element with nuclear fission, a little more dangerous, but yeah, so obviously the compression part's just the pump, the heat addition, obviously that's just the reactor, the expanding it into steam, and then heat rejection is just, when it's recondensed. All right, so this is going back to the part with the alternative fuel. So I did a little bit of research on this, and we really haven't used it in any reactors yet, but it's being tested to use thorium, which, like uranium, has a very long half-life, which is very good for nuclear reactors. But there are some problems with thorium, so you can't use thorium by itself. It's fissionable, but it's not fissile. And so what it means by being fissile, it means like basically you can fire a neutron at a low energy state, and then it'll become fissionable. With thorium, you need like a catalyst like uranium to basically fire off high energy, because it can't activate at any low energy neutron shooting at it. And then, but it's basically like people are looking at it right now. I think China tried to basically improve and actually do one. It's basically, you know, thorium's very plentiful, uranium's a lot less plentiful. So if we can make like a hybrid reactor, that could be very good for like upcoming like, you know, energy concerns. All right, and out of most of it, it's a very clean energy. Like out of most, obviously, you know, the whole thing radioactive waste, but comparatively, it's basically zero emissions. So it doesn't, obviously, I think the only emissions might be if a worker has a smoke break, but other than that, it's really not gonna have any emissions because it's all, you know, water and steam. It has a very low land to power ratio. So for the one plant, compared to other, you know, other sources of like power and stuff, maybe besides like a coal plant or something. But for a nuclear reactor, a nuclear power plant, it doesn't take up as much land as say like a wind farm or like a, a solar plant, which takes up like droves and droves of land. And the thing about that is you can't really build anything else on that land besides those power, the power of solar and like wind. As well as a little better in the, I guess, ecological department from like, I guess, water power or hydropower. Because hydropower, you basically build it, you know, on a waterfall, and then that obviously has ecological concerns and messes with a lot of fish species. And then also like with the diagram right there, uranium is a very high energy dense. And so for one uranium pellet, which is just 1 inch tall, it's equal to 12 or 17,000 cubic feet of natural gas, 120 gallons of oil, and 1 ton of coal. So it takes way less space. And although radioactive waste is kind of, you know, it's an issue and it's probably what most people worry about, there's ways to kind of make it not as radioactive. Like I said, the boron helps reduce the radioactivity, as well as I looked up a few, it didn't really explain it too much, but I know you can use reverse osmosis to then make the water, you know, reusable, safe, and even drinkable, but I don't know if I'd want to drink it. All right, that's my sources. Any questions?
No. Do you know that there's one upstream of us?
Yeah. I tried to look up what reactor it was, but I didn't know.
Did it say which one was like more efficient between the two that you showed, the pressure one or the regular?
I think they're about the same. I looked up, if you go back to, so this one. So about 2/3 use this one, and about 1/3 of reactors use that one. And of what I've heard is like water reactors are the most safe and they're the most used, but they're not the most energy efficient out of like all the nuclear reactors. There's ways, I think Adam and another thing said like liquid salts you can also do. These are just the two main ones, but there's like a list of like 40 different types of reactors, and I'm like, that's maybe not the best for a 6-minute talk. But I think out of probably this one, I would say, because it's the most used and you probably get a little bit more power, but I think most nuclear reactors work between 30 and 40%. So, anything else? All right.